Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we'll be doing Unit 3, Lesson number 9 on more work with continuity. So, in the last lesson, what we saw was the algebraic definition of continuity. In this lesson, what we're going to do is look at some of the classic theorems of calculus that rely on a function being continuous. All right? Part of what we're going to try to get through today is the idea of being able to read a theorem in calculus, or in mathematics in general, fish through all the complicated notation, and put that theorem in our own words. So we're going to begin with that. All right, the absolute Max Min Theorem. If f of x is a continuous function on the closed interval a to b, then there exists a c1 such that a is less than or equal to c1, which is less than or equal to b, and f of c1 is greater than or equal to f of x for all x in a to b, and likewise too. So one of the skills that you need to get good at as you move on in mathematics, especially in calculus, is being able to look at a theorem like this that has got, I don't even know how many letters in it, and really understand what it says in plain English. So what I'd like you to do is pause the video right now and think just about number 1. Number 2 is almost exactly the same, but think about number 1. What does that say? All right, let's talk about it. So, excuse me. Notice this will only hold if we're talking about a continuous function. So what does it say? Well, if f of x is continuous, then what must be true? Well, let's take a look at this. Lots of letters, and let's talk about how you sort through them. A C1. Now, whenever you see a subscript, that means a very particular value of a particular constant. So C1 is a constant. C1 is greater than or equal to A, which means it could be A, less than or equal to B, so it could be B. And f of c1 is greater than or equal to f of x for all x in a to b. All right, so the first thing to really understand about this is that c1 represents a specific x value. All right, it's a constant, and it's a specific constant. I just don't know what it is. This is therefore a specific y value. And look, it says there exists a specific x value such that the y value at that x value is greater than or equal to, now this is a generic y value. Is greater than or equal to all other y values or greater than or equal to a generic y value for all x values in this interval. Okay, wait a second. So there's a specific x value that lies between a and b, but it could be a, could be b, where the y value at that x value is greater than or equal to all other y values on the interval. So if f of x is continuous, there is an x value at which the largest y value occurs. You could also say that this theorem tells us that there will be a largest y value, that there'll be a largest y value. But technically speaking, what it guarantees us is that there's an x value at which the largest y value occurs. And number 2 is very similar, but just the opposite. If f of x, well, maybe not opposite. If f of x is continuous, there is an x value at which the smallest y value occurs. All right? And it's kind of neat Now, you may doubt right now why the function has to be continuous for this to be true, but we'll take a look at that sort of contingency in a little bit. The name of the theorem is exactly right on, the Absolute Max Min Theorem. It basically boils down to saying a continuous function on a finite interval has an absolute maximum and an absolute minimum. All right, so in other words, we're not letting the function go from negative infinity to positive infinity. Or, sorry, we're not letting the domain go from negative infinity to positive infinity. All right, we'll pause the video now, and then we're going to jump in and do a couple problems on the Absolute Max Min Theorem. Okay, I'm going to clear out the text. Let's take a look at exercise number 2. Consider the function f of x equals x minus 3 quantity squared minus 2 on the interval 0 to 5. Sketch a rough graph of this function over this interval and state the maximum and minimum values of this function along with where they occur. All right, so it's not the hardest problem on earth. In fact, what I'd like you to do is pause the video now and see if you can work through it on your own, and then we'll go through it. All right, let's take a look. I'm going to use my program to create a set of axes. All right, what I know is this is y equals x squared, shifted 3 units to the right and 2 units down. Oops, missed. Sorry, let's just pretend that's 2 units down. I'm going to draw in the parabola dashed. All right, because I want to go 0 to 5. So 0, 5. Now this may not be the best. This may not be the best graph. All right, but it's not bad. And one thing we can definitely tell is that my absolute minimum occurs down there. Now, what is that equal to? Well, it's equal to -2 at x equals 3. Now, I don't know. The absolute maximum is one of these two. It looks like it's at x equals 0, but let's figure out what f of 0 is. F of 0 is -3 squared minus 2. That's 9 minus 2 is 7. And let's figure out what f of 5 is. That's going to be 5 minus 3, which is 2 squared minus 2, gives me 4 minus 2 is 2. So that is my winner. So my absolute max is equal to 7 at x equals 0. Now, a couple things before we move on. A lot of students can be kind of sloppy in their thinking, their notation, and their representation. Please make a distinction between values of the function. Okay, those are y values. And where they occur. Where is almost always x values. A lot of students, they want to be lazy in their thinking. They don't want to have to read that hard. They don't want to have to distinguish between the two. So they'll say, well, can't I just say I have an absolute minimum of 3, -2, or an absolute maximum of 0, 7? And the answer is no. All right? This is the analogy I like to give. If I ask you for what the population is of the highest populated state in the United States, I want you to say 25 million. I don't want you to say California. I don't want you to say California at 25 million. If I ask you for the largest population, I want the population. If I ask you for where it occurs, then I want California. And you need to keep the two sort of straight in your head. What the maximum minimum are, those are y values. Where they occur, those are x values. Okay? It's important. It sharpens our thinking and our reading. So pause the video now and write down anything you need to. All right, I'm going to clear out the text. And let's keep going. Exercise number 3. Consider the piecewise linear function g of x equals blah, blah, blah. Sketch this function. Does g have a maximum or minimum value? If so, at what x values? If not, why not? All right, this is a nice problem. Again, you have all the tools you need. So what I'd like you to do is pause the video, do the sketch, think about absolute maxes and mins, etc. All right, let's go through it. Again, get myself some axes. Probably bigger than we need them to be, but that's okay. So let's dimension -1, 1, 1, -1. Y equals x plus 1 is going to be a line that looks like this. Y equals x minus 1 is going to be a line that looks like this. And of course the point 0, 0 looks like this. Now we've got x plus 1 from -1 to 0, so that's going to go from here all the way to here. Then we have this one from 0 to 1, and we have that. So there's our sketch. Sorry if it's not the best due to the a little dashing here. Let me see if I can get rid of some of that. And I got rid of the curve too. All right. We're okay. Let me actually fill this in maybe with a little bit of a stronger line. There we go. Okay, good. So now let's talk about, does G have a maximum or a minimum value? Now, let's just talk about the max. Okay, if it had a maximum value, if, big if, then I would assume that you'd say that maximum is y equals 1. The problem is, if it's got a maximum value of y equals 1, you should be able to give me the x value where it occurs, right? It's kind of like almost dare. It's like, well, if somebody comes along and says the maximum y value there is 1, then you should come back and say, all right, what x value gives me 1? And the answer is, oh, well, there is no x value that gives me 1. Then, of course, people get cute and they say, well, then the maximum would have to be 0.9. And then I'd say, well, no, wait a second. I can go 0.99. So then eventually somebody gets cute and says, oh, the maximum value is 0.9 repeated. But 0.9 repeated is the same as 1, okay? If you don't believe me that 0.9 repeated is the same as 1, then find a number that lies in between them. Or, better yet, right? You know, we all know that 1/3 equals 0.3 repeated. So if I multiply both sides by 3, I would get 1 is equal to 0.9 repeated. Think about it. Yeah. So what's cool about this is that this function has no maximum value. There is no maximum, and likewise, and no min. Okay, why? Because it is not continuous at x equals 0. Right, and that's where we would have had that max or that min, right? They would have occurred at x equals 0. But at x equals 0, y is 0, right? So it's not the min, right? There's no min, there's no max, which is really cool. Now, don't get me wrong. Some people make this false equivalency. They say, well, okay, if you're continuous, you must have a maximum and minimum. And if you're not continuous, you can't have a maximum or a minimum. That's not true at all. In fact, we could easily have a function that looks something like this. Right? That has a maximum right here. Has a minimum right here. But isn't continuous because of this hole sitting there. Right? Really, you won't have a maximum or minimum if you have a discontinuity at sort of the location where you would have had the max or the min, if you will. Okay? But what we are guaranteed is if we're continuous, we have a maximum and a minimum. All right. Well, pause the video now and write down anything you need to. Okay, clearing it out. And let's keep going. The next theorem we're going to look at is called the Intermediate Value Theorem. Now, this is such a famous theorem in mathematics that it is commonly abbreviated as the IVT, the Intermediate Value Theorem. All right? And exercise 4, just like exercise 1, is trying to interpret the intermediate value. So, the Intermediate Value Theorem. So what I'd like you to do is read through that theorem and then see if you can explain in your own words what that theorem is trying to tell us. All right, let's go through it. Word by word. If f of x is a continuous function, all right, there's that continuity thing, on the closed interval a to b, then for any specific y value of y, call it y sub 0, such that y sub 0 is greater than or equal to f of a, less than or equal to f of b, there exists a value of x, call it c, such that f of c is equal to y sub 0. Okay, let's draw a graph to illustrate this. Hey, it's blue now. Oh well, that's okay. Maybe I'll now do the text in black. Let's say we have a, and let's say we have b. Nice continuous function. Could have just drawn a straight line, but that's okay. So we have f of a, and we have f of b. All right. So now we're saying, look, let's say there's a specific y value that's in between these two, y sub 0. Then what this theorem says is that for any y value between the first y value and the last y value, any y value in between, there is a specific x that gives us that y. So for any y value in between the first and last, for any y value in between the first and last, there is at least one x that gives that y. All right, this is cool. Now, by the way, I just wanted to mention something. A few things this theorem doesn't say. This theorem does not say between the smallest y value and the largest y value. I kind of drew it that way. I apologize. As well, there's nothing that really says that the first y value has to be less than the last y value. But that's the way the theorem is written, at least here. For completeness, we really should also look at the second case, which is that the last y value is smaller than the first y value, but it would be exactly the same theorem. It would just have these two things flip-flopped. But really, it's kind of cool. All this theorem says is something that I think is very obvious. If you know the y value that you start at, and you know the y value that you end at, you have to hit every y value in between. So that, to me, is the easiest way of looking at this theorem. If you know the y values you start at, and you know the y value you end at, then you have to hit every y value in between if the function is continuous. If the function's not continuous, then I think we can all understand how you could have a function that comes along, has a discontinuity, and misses a bunch of y values in between the first and the last. But if the function's continuous, we have to hit every y value along the way. All right, well, pause the video now and write down what you need to, and then we'll do a few problems involving the Intermediate Value Theorem. All right, going to get rid of it. All right, exercise number 5. Show that the function f of x equals x cubed minus x minus 1 has an x-intercept on the interval -2 to 2. Fully justify your answer by citing the IVT. All right, an x-intercept. Well, by definition, x-intercept is a place where f of c is equal to 0. All right, well, let's just play around for something. Let's figure out what f of -2 is. That'll be -2 cubed minus -2 minus 1. That'll be negative 8 plus 2 minus 1 gives me negative 7. Let's figure out what f of 2 is. Well, that's 2 cubed minus 2 minus 1 gives me 8 minus 2 minus 1 gives me 5. But since f of x is continuous, as all polynomials are, right, and that's just a polynomial, but since f of x is continuous and negative 7 is less than 0 is less than 5, the IVT guarantees there is at least one x between negative 2 and 2 that gives f of x equal 0. Maybe not gives. Let's use makes. Right? So that's the key. Right, just think about it graphically. I can't go from a negative y value to a positive y value without passing through y equals 0, because this is a continuous function. All right? It's kind of cool. All right, pause the video now, write down anything you need to. Okay, here we go. Whoa. Got the afternoon yawns. Monday afternoon yawns. All right, let's do one more problem. Let's take a look at a table. Exercise 6. The table below gives selected values for the function f of x and g of x, both of which are continuous. All right, that's important. So f is continuous, g is continuous. The function h of x is defined such that h of x equals g of f of x. I think I'm going to go back to blue. All right, now, one nice theorem, or one nice thing about continuous functions, is that the composition of continuous functions, going into the black, is also continuous. All right, so the fact that f and g are both continuous means that h is continuous. Then we have this weird k value just chucked in here. Whoa, what is that k doing there? All right, anyway, you saw it. I'm going to erase it. It says, if k is equal to 2, explain why the equation f of x equals 3/2 must have two solutions on the interval negative 1 to 1. All right, here's negative 1 to 1, and I'm saying it has to have two solutions. Think about that for a little bit. All right, let's talk about it. Well, notice, to go from negative 2 to 2, we must hit 3/2. And to go from 2 to 1, we must also hit 3/2. So, because 3/2 is greater than negative 2, less than 2, and 3/2 is greater than 1, less than 2, we hit f of x equals 3/2 at least twice. On the interval negative 1 to 1. This is actually a poorly worded problem. I really should say, if k is equal to 2, explain why the equation f of x equals 3/2 must have at least two solutions. Because for all I know, it hit it again and again and again and again by doing this kind of business. I just can't tell it in the table. Now, letter B we actually already answered a little bit, and I apologize for that. It says, what do you think can be said about the composition of two continuous functions? It is also continuous. And now we see a ramification of that. Letter C says, does the equation h of x equal 3 have a solution on the interval negative 1 to 2? Justify your answer. Well, again, saying h of x equals 3 has a solution is the equivalent of saying that the graph of h of x has to cross y equals 3 at some point. So what we're going to do is we're going to evaluate h of negative 1. And what is that? It's going to be g of f of negative 1. Whoops. All right, but what's f of negative 1? F of negative 1 is negative 2. And then g of negative 2 is 5. Now let's figure out what h of 2 is. That's going to be g of f of 2. Well, let's see. F of 2 is 0. And g of 0 is 1. So, since h of x is continuous and goes from y equals 5 to y equals 1, it must pass through y equals 3 at least once. Therefore, the answer is yes. Right? Again, it's that simple. If I know the y value I start at, and I know the y value I end at, right? So my starting y value, not necessarily my max, not my min, my ending y value, right? Then I must pass through every y value in between if I know the function is continuous. All right. Well, pause the video now and write down anything you need to. All right, I'm going to clear out the text. Great. Well, today, we didn't work so much with the limit definition of continuity. In fact, we didn't work with the limit definition of continuity at all. What we did do is we looked at two major theorems, the Absolute Max Min Theorem and the Intermediate Value Theorem, that rely on a function being constant. That rely on a function being continuous. Obviously, the function doesn't have to be constant. So, these theorems, then, we got practice in both interpreting them and seeing how they break down when functions are not continuous. All right. For now, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. Until next time, keep thinking and keep solving problems.